Hi, everybody. In this lecture, we're going to be covering Chapter 2, looking at frequency distributions. Now, note that this is the first set of descriptive statistics that we'll be talking about in the course. And the goal of today's lecture is to introduce you to a couple of different ways we have for describing data. And that's by putting them into tables that are called frequency distributions. They allow us to organize and summarize our data, as well as to different graphs and plots that are available in order to graph your data and make it visually accessible. So at this point, you should be reading through Chapter 2, and I'm going to summarize some of the key concepts and key ideas here in this lecture. We'll be looking at how frequency distributions are used, what's their purpose, and what kinds of scenarios do we use these distributions. We'll learn how to create our own frequency distribution tables. A couple different forms of those exist. We'll learn about how to interpret frequency distribution data and take that same data and put it into different kinds of graphs. And finally, we'll talk about being cautious when creating and interpreting various graphs. Let me just make this full screen. Okay, so in this chapter, you're going to need to be familiar with proportions, things like fractions, decimals, percentages. These are all pretty much getting at the same deep meaning. They're just, you should be able to take a decimal and convert it into a percentage and things like that. You'll need to be familiar with scales of measurement. We've already covered that in the class, but the kind of scale that you're measuring your data on has implications for what kinds of graphs are available. Same goes for whether your variables are continuous or discrete. And the real limits of continuous variables will come into play. I'll bring that up as we go along here. But if any of this is completely unfamiliar, you want to go look at the appendix or to the appropriate chapters and polish up your skills. Okay, let's see if I can just get this to be full screen. Okay, there we go. So all a frequency distribution is an organized table. And what it's going to do is show us the number of individuals that have scored each possible value. Put differently, we're going to get the number of people or the number of cases that have scored a particular category or a particular response on the scale of measurement. Now, these can be either tables or graphs, but regardless, we're always going to have the categories that make up the scale and the number of people that fall into each category. So let's just go ahead and look at a really simple example of a frequency table. The X are the possible scores that one could have obtained. So this is some kind of assessment or test where scores can range from 1 to 5. This could be the number of mistakes made on a memory test. This could be symptoms on an anxiety scale. But right here, the possible options of scores range from 1 to 5. And if we go over to the right, we'll get the frequency, the number of cases or the number of individuals in the sample that have obtained each one of those scores. So we can see that 2 people have scored a 5, 4 people have scored a 4, 1 person has scored a value of 3, 0 people have responded with a 2. Okay, it's important that we include that even though there's a frequency of 0, because this value is possible and it's within the range of the rest of the values, we want to be honest and clear that this was a possible score, but nobody got it. Oops, and then we have 3 people scoring a 1. So this is just as simple as it gets, a straight up frequency distribution table. You have the number of people that scored the possible values on some kind of test or scale. Okay, we always have the X values on the left and the frequencies on the right. Now, a frequency table gives us a lot of information. We can actually, in addition to the frequency of scores, get some other key pieces of data. Okay, let me just go back to this table. So if I go across each row, okay, and I create a new column here, we could call this the sum of f times x. If I go 5 times 2, I get 10. 4 times 4 is 16. 3 times 1 is 3. 2 times 0 is 0. 1 times 3 is 3. If I then add all of these values up, I get the sum of all of the scores in the data, okay? The sum of the frequency times the x values. We can also figure out the number of subjects that were in a study. Okay, 2, 4, this is 6, 7, 8, 9, 10. There were 10 people in this data collection. I get that from simply adding up the frequency column. Okay, so we can get both the frequency, the total frequency in terms of how many people were in the study, what's the number of subjects, and I can also get the sum of the x values by summing up the frequency times those values as I just did. This is a way faster approach than taking all of the data out of the table. Now, typically, our frequency tables are going to include proportions and percentages because they can be easier to understand and they simplify the data. So what is a proportion? It's just a fraction of the total group that's associated with each score. Okay, so proportion is the number of people that scored that particular value over the total number of people in the study. So if I tell you that there were 10 people in the study and 5 of them scored above an 80%, well, we would have 5 over 10, 50% of the class, right, scored over an 80%. Okay, these are relative frequencies. They describe the frequency of a particular response in relation to the total number of people. Now, we typically take proportions and convert them to percentages by simply timesing them by 100. So in the example I just gave, right, we had 5 out of 10 people scoring above an 80. Okay, well, that ends up being 50% if we go through the math. 5 over 10 times 100 equals 50%. And you'll typically see this type of data included in a frequency table. Here we have our possible responses. Here are the frequency of people that scored each X value. And then we can go ahead and compute the proportion. So 1 out of 10 people had a value of 5, that's 0.10. 2 out of 10 people had a value of 4. 3 out of 10 people scored a 3. 3 out of 10 people scored a 2. And 1 out of 10 people scored a 1. Okay, we're simply taking the frequency of the response divided by the total sample size, which is 10. And here are our corresponding proportions. If we times them by 100, we get percentages, right? 0.20 squared is 20%, 0.30 squared is 30%, and so on. These should always sum up to 100%. That's a good way to make sure you didn't make any mistakes. Okay, and you can see how this table gives us an idea of, wow, this is really normally distributed data. The majority of people are scoring, you know, right in the middle, 4, 3, and 2, with fewer people scoring extreme values. Okay, let's go ahead and do a practice question here. Use the frequency distribution table on the right to determine how many subjects are in the study. Okay, if you need more time, pause the video. We just simply add up the frequency. 2 plus 4 plus 1 plus 0 plus 3 ends up being 10. Okay, just add up the frequency column and you're going to get the total number of people in the study. Okay, let's go ahead and do the first question here. True or false, using the frequency distribution on the slide, more than 50% of the individuals scored above a 3. Okay, well, if we go ahead and we look at the total frequency, we can see there's 10 people in the study. So did at least 5 of them, right? 50% of 10 is 5, score above a 3. 4, 5, 6, we can see, yes, that's the case. That is true, okay? If we look here, the proportion of scores in the lowest category was P equals 3. Well, what's the lowest category? Value of 1. We had 3 out of 10 people score a 1. So the proportion should be 0.30. Okay, here are the answers. If we take that 0.3 and times it by 100, 30% of the sample scored a 1. Value of 1, 3 people out of 10 scoring it, 30%. Okay, so you should be able to look at these tables and generate these types of conclusions. Now, sometimes we have a lot of data and we have to basically group our categories. If the number of categories is very large, we'll group them to make the table easier to understand. However, the simplicity and conciseness of the table comes at the expense of information. So let's go ahead and just look at an example of this. This is just a grouped frequency table. And as you can see, we're now giving the frequency of people that scored within a certain window or a certain range of scores. Okay, this cuts the size of the table in half because now we are including a range of values as possible response options. So I can see here that 2 people scored between a 30 and a 31. Now notice I don't know what their exact score is. I just know they fall somewhere in this window. They could have both gotten a 30, they could have both gotten a 31, one could have gotten a 30 and the other could have gotten a 31. I lose the precise estimate. If I go up here, 6 people got between a 38 and a 39, but again, I don't know their exact score. I can't retrieve those exact details. Okay, this is a grouped table. We're grouping the response options to keep the table short and concise, okay, but to still give an overall depiction of how individuals performed. You see this a lot when you have a lot of data. Okay, just a takeaway point, the whole reason we create tables and graphs is to simplify data. If your table is 2 pages long or your graph is so complicated that it takes a long time to understand it, you've kind of lost the point of making tables and graphs. These are descriptive techniques that we use to simplify data so people can look at them pretty quickly and take away some kind of big picture conclusion. Okay, so simplicity, keeping it concise is always a good thing. Here's another grouped frequency table. Here we have weekly wages. Okay, again, you can see we've grouped together various values, and you can see the number of people that are earning that range of values over here. Now, your book is going to go into depth about guidelines for constructing frequency distributions and graphs. There's a couple mandatory rules that everybody follows, but it should be noted that there are a lot of times where the researcher or the person doing the research has to make a decision of best judgment. Figuring out kind of how to group your intervals or what numbers to use for interval width, okay, how to plot your data is going to depend on how much space you have, what message you're trying to get across. So again, there's always some judgments and decisions that need to be made on the part of the researcher when graphing data. Fortunately, most statistical software does a great job of computing and producing various tables and graphs for you pretty much effortlessly. So in the statistical analysis project, you'll get to practice generating some tables and graphs using a simulated data set. But when we look at requirements for grouped frequency distributions, we want the intervals to all be the same width. Okay, so you can see here there's a 1 point difference between each possible option. We wouldn't want this to be inconsistent. We wouldn't want this to say 30 to 31, and then this says 32 to 40. Okay, we want to keep the gap the same across all of the intervals. Okay, you can see the same thing here. We have that 1 point gap. Okay, that's consistency in interval width. We also want to make we just want to make things simple. Okay, we don't want to use weird or awkward numbers. We want to use things that are easily divisible, 2, 5, 10. I think a lot of this stuff is common sense when you're graphing it. We don't want to use, windows that are 1.5 or something complicated to understand. Okay, we don't want to really ever go for more than 10 possible class intervals. But again, you need to use your best judgment depending on the data. And again, always choose simple numbers. Here's an example of computing a frequency distribution for a discrete variable. So far we've been talking about continuous numerical variables. Here we have method of birth control. This is nominal data, okay? This is non-numerical data. And these are the number of people in some kind of study that are subscribing to being on that method of birth control. And we can total them all up to get the total number of people in the study. The score is an exact score. Individuals with the same recorded score had the exact same measurement. Okay, abstinence, 14 people all scored abstinence. Basically, computing tables for discrete variables is really simple. It's just simply the possible categories and how many people fell into that category. Now, when we are constructing frequency distributions for continuous numerical variables, we need to remember real limits, okay? This has been introduced previously, but remember, if somebody scores a 90, that includes scores of 89.5 all the way up to scores that fall below 90.5. So there's some rounding there. And individuals with the same recorded score, if we say they got a 90, there still might be some slight variation in their performance. Somebody with a 90 could have had an 89.8, or they could have had a 90.2, and they were both rounded to the 90 mark. Okay, so let's go ahead and see if we can apply this. A group frequency distribution table has the following categories. What is the width of the interval from 20 to 29? Now, it might be really tempting to say, oh, duh, it's 9 points. But that's not the answer. It's 10 points because we need to consider the real limits of the interval. Okay, the upper real limit is 29.5. Anybody below 29.5 has been put in the 29 category, and 19.5 is the lower limit. If you scored a 19.5, you are getting scored as a 20. So this actually encompasses 10 full points. Okay, just remember you have to keep into account the rounding, and that's going to be important for graphing data. Okay, a couple more questions. The first one here, true or false? You can determine how many individuals had each score from a frequency distribution table. Okay, that is of course true. A frequency distribution table gives us every possible response option and shows us the number of people that scored that value. However, in a grouped frequency distribution, we cannot figure out the exact score because we lose that precision. Okay, we can only see the number of individuals that fall in that class. Okay, so let's go back and look here. I can tell you that 49 workers earned between 38 and 39 in currency. I can't give you the exact amount. I don't have that data. Okay. Frequency distributions give us all of the data and details, but when we have big data sets, we may have to sacrifice some of those details by grouping up our possible response options and creating a group frequency distribution. Concise, simple, but we lose some of the details. Okay. Here is an example of how we can take frequency data and graph it. So over here on the right, you're seeing a very simple frequency table. Here are the possible values and the number of people that have scored that value. Now we can graph this, and this is what we call a histogram. Okay, we always put frequency on the y-axis, always on the y-axis, and the x-axis is always the scores or the responses. In this case, it's the number of correct items on a quiz. So notice we have one person scoring a 1. That's consistent with what this table says. 2 people scored a 2. Okay, 4 people scored a 3. 3 people scored a 4. And 2 people scored a 5. Now, real limits are important because notice that for the value of 1, I'm starting my graph at positive 0.5, negative 0.5, or sorry, positive 0.5, and it's going up to 1.5. Okay, that's because the value of 1 has a lower real limit of 0.5 and an upper real limit of 1.5. The same can be said for the value of 2. The lower real limit of 2, the lower real limit of 2, right, is 1.5, and the upper real limit, 2.5. So when we graph continuous numerical data, we have to make sure that we are graphing with the real limits in mind. Basically the -5 below and +5 above. Now these bars are all connected because this is a continuous numerical variable. Here is what we call a polygon. It's the same thing as this, but instead of bars, we're swapping them out for dots. Okay, so we have a dot showing that one person scored 1, 2 people scored 2, and so on. Okay, this is a polygon, and we always want to connect the dots and make sure we start and close our polygon. So once we finish connecting the dots, we bring the bar down, or the line immediately down to the next value. So here's just another descriptive statistical technique, a polygon. You can easily see that the majority of people scored a 3, with fewer cases of individuals scoring in the extreme low end or high end of this quiz. So again, with graphs, you have to use your best judgment, but all graphs should have 2 axes. Our x-axis typically has the categories of the measurement scale, the scores, the raw values, and they should increase from left to right. And the y-axis always has the frequencies. They should always be meeting at the 0 point. And typically your height should be about 2/3 to 3/4 of the length. Okay, again, that's just kind of a stylistic thing, and computer software will automatically do that for you. So when we're graphing data, we have to ask ourselves a couple of questions. What is the level of measurement that our variable has been measured on? Do we have nominal label category data? Are we asking people if they're male or female? Are we asking them what color hair they have? Do we have ordinal data? Do we have rankings? Do we have interval data, right? This is numerical data with an arbitrary 0 point. This is the most typical kind of data we have in psychology, or ratio data. Now, numerical data is going to be graphed fairly similarly, but the really key difference here is if you have nominal data. Okay, if you have regular categories or labels, you have to use some different graphing methods, which we'll talk about in a moment. Is your data discrete? Do you have black and white categories or black and white values where a person is either in one or the other? Or do we have continuous data? Does our data contain decimal points? Are we talking about samples or populations? The answers to these questions are going to determine what kinds of tables and graphs you should be using. Okay, so a frequency distribution histogram requires that we have numerical data, and it could be interval or ratio. And basically, this is just like the graph we just saw. The bars are drawn above each score, and the height of the bar corresponds to the frequency, and the width of the bar takes into account the real limits of the interval. We always want to include scores with a frequency of 0, to be honest. Let's look at one. Here it is again. We've just looked at this. This is a histogram, your typical frequency distribution histogram. You couldn't use this kind of graph if you didn't have numerical data. We can also make histograms for grouped frequency tables. Okay, the only difference now is that the bars represent an interval. This is fairly uncomplicated. We just need to keep in mind that each bar represents a window of possible values. In this case, we have children's height in inches. Okay, you can see here's the original frequency table. One person is between 44 and 45 inches. Two people are between 42 and 43, and so on. Here's our frequency on the y-axis. And this little gap here is just telling the audience we skipped a whole bunch of values and we started our graph at 30 because we had nobody in our sample that was below 30 inches. And if we included all those values that nobody scored, our graph would be really long and complicated, and it wouldn't be concise. Now, if somebody scored a 0 somewhere within this range, let's just say we had no people between 36 and 37, we would still include this in our graph, and we would note that the frequency was 0. So somebody might be asking, didn't you just say that even if people scored 0, we should still put them in the graph? Yes, we should, but if there is nobody scoring any values for a whole bunch of possible options below a certain point, we just let the reader know we've skipped those values for simplicity. Nobody scored them. We're starting at the 30-inch mark. Okay, and if somebody, if for values 36 to 37 inches, we actually had no cases falling in that range, we would still include that and just show that it was at 0 frequency. So we include 0 frequency when it's within the range of our other values. Okay, for honesty. Here's another kind of graphing technique we have. It's called a block histogram. Each block represents one case. Okay, this is concise because it shrinks the size of the y-axis. So one person scored a 1, 3 people scored a 2, 3 blocks, and so on. Each block is a case. This is a block histogram. If you have a really large set of data, this might not be the best way to go because you're going to have to put in hundreds of blocks. But for a small set of data, this can be pretty efficient. You don't see these as commonly as regular histograms, but they are out there sometimes. Okay, polygons. We've already looked at a polygon, right? The different lines with the dots. And we basically have a dot at the center of each interval. Okay, we can also use them with grouped frequency data. Let's just go ahead and look at that polygon again. Okay, one person with a 1, 2 people with a 2, 3 people scored a 4, and so on. And then we connect the dots and we make sure to close our polygon off by just bringing the line down to the x-axis. Here is an example of a polygon for grouped frequency data. Here's our frequency data here on the right. 4 people are between 12 and 13, 5 people between 10 and 11. We just make sure that when we graph, we put the dot right in between the interval. So between 4 and 5, we put it at 4.5. Between 6 and 7, that dot would go at 6.5. Okay, so it's the same concept. You've just got to put the dots in the middle of that interval. Okay, same thing, connect them and close them. And look at this, it gives you a really easy to take away visual of how people scored on this assessment. I think that graphs are easier to interpret than tables. I think you see more graphs than tables typically in research. Okay, summarizing the data for us. Really helpful when you have large data sets. Now, how do we graph nominal and ordinal data? We have to use what's called a bar graph. Okay, it's similar to a histogram. The only difference really is that we have spaces between the bars to indicate that we are talking about discrete and separate categories or types. Okay, here is a bar graph showing the frequency of personality types. So maybe I took a sample of students and I gave out a personality test, and 10 students were classified as type A, 5 as type B, and 20 as type C. Okay, different types of personality. We have spaces between the bars to indicate that we are in fact talking about different types. As usual, frequency stays on the y-axis. Okay, so a histogram is for continuous numerical data. The bars are all together. When we have nominal categorical data, we use a bar graph and we put spaces between the bars because these are not numbers and this is not a continuous variable. These are different types of personality. Let's go ahead and look at population graphs. Okay, this is going to be more important as we move on in the course. When the population is small, it's easy for us to make a histogram. But when we have a really large population, scores for each member are not possible. And instead, we're going to be graphing data based on what's called relative frequency. And our graphs will use smooth curves to show us exact scores were not used, okay, that we're looking at relative frequencies. Now, the normal distribution is a very common distribution shape. Okay, it's symmetric with its greatest frequency of scores in the middle, and it's common. It's a common data structure for many variables. Many of our statistical techniques in this course assume that our data is normally distributed. More on that in a moment. Okay, here's an example of a bar graph showing relative frequencies. Individuals were going out into a lake, and they wanted to see the type of fish that were present in that lake. And here's what you have on your y-axis. We now have the relative frequency, okay, because there could be thousands and thousands of these fish. But from a couple of sampling tests, we have concluded that there are twice as many bluegill as bass. Okay, relative frequency. There seems to be twice as many bluegill as there are bass. Okay, spaces between these bars, these are different types of fish. Here is the normal distribution. This is an example using intelligence tests or IQ scores. Okay, IQ scores are part of a standardized distribution. You can take any IQ test that's valid and shown to be reliable, and we can convert your score and plot it somewhere on this normal curve to see how you fall compared to the rest of the population. The average IQ score in humans is 100. And the standard deviation, we'll talk about that later in the class, the average spread between scores is about 15 points in each direction. So here we have frequency on the y-axis, and you can see that we don't have as many people scoring extremely low, and we also don't have as many geniuses. Okay, most of us are going to be somewhere in the middle in terms of our intelligence. This is a normal curve. The majority of cases fall near the average, with fewer moving out to the extreme tails. Now, graphs can be used and misused. You see this all the time, and the goal of this class is to make you much more statistically literate and skeptical at the same time. Here's the same data plotted in two very misleading ways. Over here, you'll see the number of homicides on the y-axis and the year from 2005 to 2008. Now, if you look at this graph, you'd be likely to say, wow, homicides are really going up. We need to do something about this right now. But when you actually look at the scale here on the y-axis, it's mislabeled the way this is set up. Okay, it's making it seem like there's much more of a jump than two people. Okay, there's really only an 8-person difference here on this y-axis. And of course, every life is important, but in a big city or a town, this may not be statistically significant. Okay, this graph, the labeling of that y-axis is making you think that homicides are increasing drastically when that's really not the case, when we really zoom in here and look at the y-axis. Now down here, this is equally misleading. This is the same exact data. In this case, the y-axis is so spread out that it makes it look like nothing is happening, okay? Now you can see that it basically looks exactly the same going across here. Okay, so the correct graph would probably be something in between these two extremes. Here, the y-axis is way too large in terms of its intervals and its widths, and here it's way too dramatic. So when you're looking at graphs in the media, advertising, research, you really want to zoom in and look at these axes. What are they measuring? And you know, is it being fairly depicted, or are they trying to get you to think that there's a bigger jump or a bigger increase than really exists on whatever variable you're looking at? You know, if I was to, you can imagine that I'm somebody advocating for interventions in a city to reduce homicide. Well, if I wanted to get that funded, right, it might be more in my interest to present data this way. Okay, but this is misleading. If I was against funding that program, well, this data would make people think that nothing interesting is happening and we don't have to worry about it. Okay, both of these are misleading because of the way the y-axis is set up. Okay, a little bit on the shapes of distributions. Researchers describe a distribution's shape in words, and we often talk about something called a symmetrical distribution, where each side is a mirror image of the other. There are also skew distributions, where scores will pile up on one side or the other. Okay, here's a perfectly symmetrical distribution. This is what we call a bimodal distribution over here. This is also symmetrical. If I fold this, it will be a mirror image of each other. You might imagine this is data on exam 1 performance. Here are the people who studied, and here are the people who did not study. Okay, some kind of bimodal distribution. There are 2 peaks in the data. This is a positive skew. The tail lingers out in the higher numbers. This is a negative skew. The tail of the curve lingers out into the lower numbers. Sometimes we get positively or negatively skewed data, and graphing our data allows us to get a depiction of whether we have normal symmetrical data or whether we have skewed data. If we have skewed data, there are various ways that we can address that. Okay, we might collect more data to normal outer distribution. There are different kinds of transformations that exist in computer software. There are various options for dealing with this. We might want to remove extreme scores or outliers that are pulling our data one direction or another. We do have ways of handling this, but for now, you should just be able to identify a symmetrical distribution compared to a positive skew and a negative skew. Okay, so here's a image. What is the shape of this distribution? Okay, hopefully no one thinks this is symmetrical. Okay, you should be answering with C, positively skewed. We have our tail piling out or reaching out to the positive higher end. Okay, a couple more questions. True or false? It would be correct to use a histogram to graph parental marital status data, single, married, divorced, from a treatment center for children. Okay, that is false. A histogram is for continuous numerical data. Those values there, marital status, that is nominal data. You would want to use a bar graph. Okay, a bar graph would be required there, and you would have spaces between each bar. However, you could use a histogram to graph the time children spent playing with other children. Okay, time is a continuous numerical variable, and we could use a histogram in order to plot that data out. Okay, so this is a fairly straightforward chapter. You've been introduced to our first set of descriptive statistical techniques, creating frequency tables, as well as different kinds of graphs and plots for our data. At the end of the day, we want to keep these as simple as possible and easy to understand. We want to make sure that we're giving the audience and we're giving the reader a summary of how the data came out. They should be able to walk away with some kind of conclusion or takeaway point by looking at your tables and graphs. That is the whole point of creating these things. Okay, the purpose of constructing tables and graphs is to simplify data. We want our tables and graphs to be as concise as possible while maintaining accuracy. And remember, judgments about table and graph construction should be made carefully. Your decisions will depend on the actual data that you have to work with. Okay, so that is going to wrap up this chapter. I have all of the notes posted here online, and you should have read the chapter or you should be reading it as well. But again, focus on what I've covered here in this video, as those are going to be the main ideas that will be presented in the exams. Okay, thanks, and see everybody soon.